in yesterday's class, what we started looking at is that we want to solve this system of linear equations Ax is equal to b for certain matrices A of the size m by n and a given vector b which is of the size Rn. So we already have understood the uniqueness and existence of the solution, the results, their equivalences that we already have understood. Then we started trying to draw analogy between inverse of a matrix and inverse of a number, right? So the motivation was if you have a single scalar equation like this, scalar equation, then what do we have? We can write down x is equal to a inverse b or 1 by a into b, and that we can do provided that a is not equal to 0. So this is the scalar equation, and the linear equation system of linear equations is the vector generalization or vector analog of this scalar equation. So what we were trying to do, we were trying to come up with an analog for this particular inverse concept of inverse in matrices, and we can say that for tall matrices, left inverse can be the concept which generalizes inverse of scalars, right? So this is the concept that generalizes the concept of inverse of scalars. And what is the, like, a not equal to 0 is something that we have here. Similarly, the columns of the matrix, say the tall matrix, should be linearly independent. That will be the concept. Okay, so this will so 1 by a will be here, and this concept a not equal to 0 will be linear independence of columns, right? So this will be linear independence of columns. Mind you, we have not shown the other way implication. We just have shown that if A is left invertible, then the columns are independent. We have not shown if columns are independent, then A is left invertible. Okay. So we will show that, but before we show that, I want to define equivalent similar concept of left invertibility. So I'll define what is a right inverse also. Okay, so the reason to do this right inverse, because you know the matrix multiplication is not commutative, then like in case of scalars, a inverse b was same as b a inverse, right, which is nothing but 1 by ab or b into 1 by a. All these things are same. That means that scalar multiplication is commutative, but unfortunately the matrix multiplication is not commutative. And I think the reason why matrix multiplication is not commutative, can anybody tell the reason why is matrix multiplication not commutative? Yes, anybody?
Because due to dimensions.
Due to dimensions. Okay, the first thing is matrix sizes. So if the matrix sizes are fine, like if you have a matrix size like square matrix, then what will happen? Will the matrix multiplication commute? Will it commute? For square matrices, can you say AB is equal to BA always?
No, sir.
Why?
Sir, matrix multiplication is not commutative.
Yes, so I am asking why.
Oh. So we can say that when we are multiplying A by B, the columns are basically in the column space of A matrix, uh, whereas when we are doing BA, it's in the column space of B.
No, that is, I don't think I understand what you just said.
So during multiplication, if we go by taking the first row of first matrix and the first column of the second matrix, these vectors need not be same when we reverse them. there is a possibility that after doing computations, it could come out same, but it is not necessary.
So what you are basically telling me is that you write down the formula. So C is equal to AB, C is the product. So Cij you are telling me is in a product of ith row and jth column, right? When you multiply A with B, and when you multiply B with A, then it's the ith row of B and jth column of A. These two products need not be same. That's why you are saying that the multiplication is not commutative, which is fine, which is correct answer. Yeah, this is correct answer. But can you think of a better way of explaining this, like one line reason why this will not be true? So you already saw one of the lectures, right, that I shared there. What was discussed? What are these matrices? They are linear functions, right? So a matrix is basically a linear function from Rn to Rm, right? So if m is equal to n, then it's a linear function from Rn to Rn. Then what would product AB really mean? What is the product AB? Have you ever wondered why the product is defined the way it is defined? It is such a complicated way to define product, but have you ever wondered why that happens? How that definition actually comes out to be? You have not seen? You don't know? Okay, so this you will see in one of the lectures that I will share with you today. So this matrix multiplication actually is same as function composition. So the definition of matrix multiplication that you see is actually, inspired by composing two linear functions. So when you compose those two linear functions, what really happens is you are basically doing matrix multiplication. The matrix representation of the linear function you are looking at, and you are getting matrix multiplication. So that comes naturally. And in general, function composition is not commutative. G composed with F is not same as F composed with G. And that's what you are basically doing when you multiply AB and BA. So that's why matrix AB multiplication is not equal to matrix BA. Okay. And that covers all possibilities. Like otherwise you have to algebraically say independently that matrix dimensions may not match. Even if they match, then there is a problem, like if this sum, this in a product will not be equal to that in a product and things like that. Okay, so all these things you need not say, just say that function composition is not commutative in general, and matrix multiplication basically is composition of two linear functions. So that's why matrix multiplication does not commute. Okay, and that's why we will define right inverse also, and then we will see what really happens. Okay, so let us write down the definition. So these discussions will be there in the lecture that I will provide. This is something that you are supposed to know already. If you don't know, you can view the lectures that I will share. Okay, so a matrix X satisfies AX is equal to R, then X is called as right inverse of A. Okay, and matrix A is called as right invertible. So this is something that, so the immediate observation here is what is the relationship between left and right inverses. Okay, so let A has right inverse B. Okay, so if A has right inverse B, then you can write AB is equal to identity. But what is AB is equal to identity? This will imply that B transpose A transpose is equal to identity transpose is equal to identity. So what does that mean?
B transpose.
So that means, correct, B transpose is a left inverse of A transpose. So this is a left inverse of A transpose. Correct. So this is what is really happening. So if matrix A is, so if matrix is left invertible, so A transpose is left invertible because left inverse exists. What do you know about the columns of A transpose? The columns of A transpose are linearly independent. So here what you will have, the rows of A will be linearly independent, right? Columns of A are rows of columns of A transpose are rows of A, right? So if right inverse exists, then the rows are linearly independent. So equivalent result of existence of right inverse we will show is that if the rows of A are linearly independent, then and only then the right inverse of A will exist. Okay, so that is something that is immediately clear. And now from here, the row independence thing, that other thing also is clear, is that right inverse will exist only for the type of matrices which are wide or square, right? Because left inverse exists for the matrices which are tall or square. So the right inverse will exist only for the matrices, because you have that implication that right inverse exists. What does that mean? If it exists, then according to the result that we already proved for the left inverse, rows of the matrix are linearly independent. So if the rows of the matrix are linearly independent, what does that mean? How should be the size of matrix? By that basis dimension equality, that one that you had already seen, you should have less number of rows than columns, right? That is how it should be. And there is this other way implication also, which is true, but I will prove it little later with the interesting matrix construction. Okay, so both way implications are true, but I will do it little later. And immediately, why we are talking of these left and right inverses? Because we want to see if they can be of any use to us when we are solving the system of linear equations, right? So can we solve system of linear equation with right inverses? Okay, so consider m linear equations in n unknowns. So ax is equal to b. Okay, application to solving systems. Okay, application to solving system. That's what we are interested in. So what will you do? You tell me. We suppose that A is right invertible. Then what will you do? Can you tell? What will be the choice of X in terms of right inverse of this? So let B be the right inverse. Let B be a right inverse. Then what happens? What will be the choice of X, the solution?
Sir, it won't be unique.
We want a solution. We are not interested in the solution. We just first want to find a solution. So what will that be?
C into B. We'll write A to C. A into C is equals to I. Then we'll write multiply by B. Then we'll get A multiplied by CB is equal to.
No. So what is the solution X? What is the choice for X? So that you tell, then we will write how we want to write it.
B capital V.
Yes. The right inverse multiplied by small b.
Okay, so you take X is equal to B into B, BB, okay. So what will this imply? This imply that AX is equal to A into B. This is AB into B. This is equal to identity into B is equal to B. So AX is equal to B is satisfied in this particular case for this particular choice of B. This particular choice of X, right? So that means that you have a solution. The solution exists in this particular case. Ax is equal to B, solution exists. So what does it mean? It means that if A is right invertible, then solution will always exist. But this is one of the solutions possibly. You consider second right inverse, because right inverse is not unique. You consider another right inverse C. Then you take X is equal to CB, and then possibly that also satisfies. So that is another solution that you may have found out. So the solution may not be unique, but if A is left invertible, A is right invertible, then in this particular case, you see the solution always exists. So what is the situation we are in? We are saying A is right invertible. That means that the rows of A are linearly independent. That is something that we already know. Rows of A are linearly independent. That means that the system of equations that you are looking at are either square or they are wide, right? So they are square systems or they are underdetermined systems. That's what you are really looking at. And in case of an underdetermined system, if your matrix is full row rank, okay, if your matrix is full row rank, we are assuming that matrix is right invertible. So if matrix is right invertible, then the matrix is full row rank, then we are saying that we will always have a solution to this system of linear equation. This system of equations is always solvable if A is right invertible. And now when we prove the other part of equivalence, that rows of matrix are linearly independent that imply that right inverse exists, then we'll show that if the matrix is full row rank, then the solution will always exist, right? So that is something that is really very important. So these results you may have already seen, but you may not have seen them in terms of this left inverse and right inverse. Okay, so this is something that is really very important. So this BB, okay, so right inverse multiplied by the right hand side, okay, that will give us the solution. Okay, that will give us a solution. So a simple example, I think this is from the book. So the matrix that we have is -3, -4, 4, 6 and 1, 1. Okay, this is from the book, and I think I yesterday already gave a couple of inverses. So this is 1/9 into -11, -10, 16 and 7, 8, -11. And the second inverse that you can think of, the left inverse for this matrix is half times 0, 0, -1, 1, 6, -4, right? So the idea in computing the second one is that you just look at this particular block, okay? You just look at this particular block and you find the inverse of that block which has been put here. So this is the inverse that you put here. So you'll get identity, and the first row you multiply by this 0. Okay, so that's the idea that they have used to compute this inverse. And because this is full column rank matrix, A is full column rank, the rank is 2, you can take any 2 by 2 minus like this and you can construct left inverses in that fashion. Okay, so that is what they have done. So this is something that you can do. So now quickly you can check. So the first point that you can check, is that for B is equal to 1 minus 2, 0. Okay, for B is equal to 1 minus 2, 0. AX is equal to B has a unique solution. Okay. This has a unique solution. Why am I able to say that it has a unique solution? And then how will I compute this unique solution? Can you tell? And how do I compute this unique solution? Okay, so the unique solution is 1 minus 1. Okay, so the unique solution is 1 minus 1. That means that 1 minus 2, 0, this vector B is this X linear combination of columns of A. And you can check the uniqueness because they form the basis of the column space, and B is in the basis, B is in that column space. There is a unique linear combination. And in fact, how do you compute this X? You can compute this X by computing B into 1 minus 2, 0. And you see that this actually turns out to be the same thing. You multiply C and 1 minus 2, 0, you will still get the same solution. So this is the way we will compute the solution, right? Yesterday we saw, if you have a left inverse, so where did I write it in yesterday's class? So yeah, somewhere we wrote down, right? If you have a left inverse, then what happens? The solution is given by this, right? The solution is given by this. This is the guess. You multiply left inverse times the right hand side, that's the guess. So if the solution exists, then that's the solution. So we know the solution exists, so that's the solution, right? So this is the solution that you obtained for this particular problem. So what is the solution for the overdetermined system? So what is the overdetermined system? One example that we saw does not have solution. So suppose you take B to be equal to 1 minus 1, 0. Yesterday we saw one such example. Then this 1 minus 1, 0, for this AX is equal to B does not have a solution. Okay. So we saw similar example yesterday. We constructed that example and we saw that solution does not exist. So how do you check the solution does not exist? You have a left inverse. You take that left inverse and you multiply B to that left inverse, right? So you will consider B into 1 minus 1 0, and you see that for this choice of x, for this x, you do not satisfy the equation, so you will show that the solution does not exist, right? And now you see, I will consider this system, so I'll just take A transpose, okay? So A transpose Y is equal to 1 2. That is the system that I'll take. So A transpose now is a fat matrix, right? So what was A? So I will take that A transpose. So the first row will be minus 3 4 1, and the second row will be minus 4 6 1. Okay, so this into y1 y2 y3 will be equal to 1 2. That's the system of equations I'm trying to solve. And now what is the solution? We just saw the solution will be, so what are the right inverses of A transpose? Since B and C are left inverses of A, B transpose and C transpose, B transpose and C transpose are actually right inverses of A transpose. Correct. So what are the solutions? So B transpose into 1 2. This can be a solution. So this is one solution. Similarly, C transpose into 1 2. This will also be the solution. And you can see that these are two different solutions. So these are two different choices here. Why? So y is equal to this is one choice, y is equal to this is another choice. These are the two different possible solutions to this system of underdetermined system. Okay, so this is underdetermined and this is overdetermined, right? So 1 and 2, these are overdetermined. So these are the solutions. So that is what is really happening. Okay. So now you see the matrices which are not square, they have either left or right inverse. But if the matrix is square, then it can have both left as well as right inverse, right? Because the dimensions match. Left inverse exists implies that the columns have to be linearly independent. So in a square n by n matrix, columns still can be linearly independent. So for a square matrix, left inverse can exist. By the same logic, for the square matrix, right inverse can also exist. So what happens to these left and right inverses for a square matrix when they exist? So that is what we really want to look at. And then that gives rise to the concept that I think everybody in this class has already learned, which is called as inverse of a matrix. Okay, so let us come to this.
Sir, I had a doubt.
Yes, yes.
So in the first example, how did we determine if the solution was unique?
So the solution is unique because I determined it by observation. Okay, in general, that will be something that you will have to understand. Okay, so I'll tell you. So the first observation I made was that if I subtract column 2 from column 1, I get the right hand side. That's it. So I know that 1 minus 2 0 is a linear combination of columns of the matrix A. That is my first observation. Okay. What is the second observation? Second observation is that right inverse exists for this matrix A. So if the right inverse exists, then what happens? Right inverse exists implies that the columns are linearly independent.
Right.
So if the columns are linearly independent, then they will be the basis, they will form a basis for the column space.
Right.
Is that okay?
Right.
And I already know that B belongs to the column space of A. How do I find out? Even if I cannot observe, once I know that the right inverse exists, then the columns are linearly independent. They form a basis for column space. And if this particular choice, B into the right hand side, the right inverse, the left inverse into the right hand side, if that satisfies the solution, then I know that I am really saying that the right hand side, B, is a linear combination of columns of A. Because it's a basis linear combination, it has to be unique, right? So the solution will be unique.
Okay.
Is that okay?
Yes.
Yeah, it's just the simple like understanding. So once you know that the right inverse exists, And once you know that the solution exists, then it has to be unique because of this logic. But that is not true for the underdetermined systems. As you see, right inverse exists means that you get only one possible solution. There might be many more. Corresponding to each right inverse, there will be a solution. Okay. So that's something. Is that clear, Parth?
Yes.
Okay. So let us move to this concept of inverse. Okay. So what is inverse? So suppose the matrix is such that it is left as well as right invertible. Suppose a matrix is left as well as right invertible. Then what happens? Okay, so then what happens? So suppose this matrix I will call matrix A. Okay, so if it is right invertible and left invertible, so I can say AX is equal to I, and I can say YA is equal to I. So Y is the left inverse of this matrix and X is the right inverse of this matrix, right? So this is right inverse and Y is left inverse, correct? Now I do something interesting. Okay, so what do? I start with X. Okay, I start with X. X is nothing but I times X. I can write this. For this I will write down YA into X. Correct. I will do this. After this, I can write down Y into AX. So why can I write this? So this is something that is really very important. Okay, why can I write? Why I can change the order in which I can multiply the matrices? So this property of matrix multiplication, the one I have used is called as associativity, right? So this is associativity. So matrix multiplication is associative. This is something that is really very important. Okay. So associativity of matrix multiplication again follows from the associativity of function compositions. Function compositions are always associative. So that's why this is allowed. And this is something that will be very useful. So this is something that you will see is a very trivial property, but computationally can be amazing. Okay, so we will come to that later. If I get a chance, I'll tell you. But this is something that is really very important for us right now. What is important is that you can write this down as y into I, which is equal to 1. So what did I just show here? I started with X. I started with X and I did some manipulations. So this is the chain of manipulations I have. And then I arrived at Y. So what I'm saying is that every right inverse is the left inverse. Correct? Every right inverse is the left inverse. So the right inverses and left inverses of the matrix A are same if A is both left as well as right inverse. So this is something that is interesting, right? So you have seen left inverse exists, but right inverse may not exist. You have seen right inverse exists, but left inverse may not exist for such a matrix. You have seen. But if there is a matrix for which both left as well as right inverse exist, both left as well as right inverse exist, then those inverses are actually same. Every left inverse is a right inverse, every right inverse is a left inverse. And what we will prove is not only this is true, left and right inverse is unique also. Okay, so here in the previous case, when the only left inverse is existing, you have seen that there will be infinitely many left inverses, or the right inverse exists, there will be infinitely many right inverses possibly. But here, if the left and right both inverses exist, then that inverse is actually unique. How will you prove that? So suppose x tilde, you can consider this, suppose x tilde be another right inverse. Correct? So x tilde is another right inverse, then what we know is ax tilde is equal to identity, and ya is equal to identity, and ax is also equal to identity, because x tilde is another right inverse. So these identities are already known. And instead of x, now I start with x tilde. So I can do the same calculation with x tilde. Then this is ya into x tilde. Then this is identity into, How would I do that? Then I'll use associativity. With the associativity, I'll show y into ax tilde, which is nothing but y into identity, which is equal to y. But we know that x is a right inverse and y is a left inverse, right? We already know that x is left inverse, y is right inverse. So we have already shown that every left inverse is a right inverse. So y is actually equal to x. So we have actually shown that x tilde is equal to x. So if we know x tilde is equal to x, then you cannot have two different right inverses. So you have only one right inverse and you have only one left inverse, and that right inverse is exactly same as the left inverse. So you have only one inverse. Okay, so that's why the case where you have left as well as right inverse, we don't distinguish between them. We just say that we have the inverse. Okay, so what is the property of that inverse? The property of that inverse is that you will have a into x is equal to identity, x into a is equal to identity. That is how this inverse will work, and that's why we can use the article the inverse of a matrix now when the matrix is left as well as right inverse. Is the argument clear? The concept of inverse, how we are coming up from left and right inverses. This argument, both these equations, I hope, are they clear? So the
Yes, sir.
second equation means that left and so left inverse is unique, right? Left inverse is unique. Okay, so I have right inverse, so I'll write right inverse is unique, but that will mean that left inverse is also unique, right? So these two statements are saying the matrix, if it is left as well as right invertible, the matrix in fact has the same left inverse and right inverse, which is unique. So we'll call such a matrix invertible. And clearly, what will be the dimension of this inverse? Because matrix is left invertible, it can almost be a tall matrix. Because matrix is right invertible, it has to be a wide matrix. So tall is equal to wide means it has to be a square matrix, right? The number of rows should be equal to number of columns. Okay, so you should have this. And then because we have shown that the inverse exists and is unique, we'll use the notation symbol A inverse, which is same left as well as right. Unique left as well as right inverse. Unique left as well as right inverse. And then if the inverse of the matrix exists, then the matrix is called as invertible. Okay, invertible or non-singular. If the inverse exists. Okay. Otherwise, the matrix is called as non-invertible or singular. Okay, so if the inverse does not exist, then it is non-invertible or singular. So this is what we have. And now why we are talking of all these things? We are talking of all these things because we want to solve the system of equations, right? Solving the system of equations. So what happens in this system of equations? Okay, what happens in this system of equations? You have the system of equations, say x is equal to b. If the matrix A is invertible, then what will you choose x to be? Choose x to be A inverse b if A is invertible. Correct? So if A is invertible, you choose x is equal to A inverse b, and that A inverse b will be the solution. A inverse b will be the solution of this particular, right? So is that okay? Do you understand this? Any doubt? Then we'll quickly show something which is even further interesting. Okay, so we have defined the inverse and we have done this. So let A belonging to Rn by n be a matrix which is left invertible. Okay, so this is a matrix which is left invertible. So if this is a matrix which is left invertible, can we say that this matrix is right invertible also?
But since the dimensions are same, we can say it is also right invertible.
But strictly speaking, how will you do that?
It's a square matrix, so left left inverse is equals to right inverse.
No. So that is the mistake that you should avoid. So what we have said, even if a matrix is a square matrix, even if a matrix is square matrix, it might happen that I never said that left invertibility implies right invertibility. Here, what did I start with? I said that if the matrix is both left as well as right invertible, I am not sure if the matrix is left invertible implies matrix is right invertible in case of square matrices. I'm not sure of that. So I just want to prove actually that it's true. So what does this mean? This means that columns of A are linearly independent. This much we know, and this is acceptable to everybody. We have shown that the columns of A are independent.
Yes.
So this means that these columns form a basis of Rn. The columns of A form a basis of Rn. And you can view A as a linear transformation from Rn to Rn. You can view A as a linear transformation from Rn to Rn. Okay, and the columns of A are forming bases. So what I am really interested in looking at is every vector in Rn. This means every vector in Rn can be written as a unique linear combination of columns of A. Is that okay? So because every vector in Rn can be written as a unique linear combination of columns of A, I will choose very special vectors in Rn. Can you guess which vectors I am going to choose? Remember what I want to prove? I want to prove that if A is left invertible, that implies A is right invertible also for a square matrix. I want to prove right invertibility. So in some sense, what I really want to show, I want to show that there exists a matrix B such that AB is equal to identity. And what I know is that columns of A are bases. So every vector in Rn can be written as a unique linear combination of columns of A. So what special vectors I will choose in Rn to show that there exists a B such that AB is equal to identity? Can you guess?
Rows of
The columns of the identity matrix.
Correct, columns of identity matrix. So in particular, excellent. So I will look at identity matrix. In particular, consider EI. Okay, consider EI, ith unit vector, right? So this is the ith column of identity matrix. Ith column of the identity matrix, correct? Because this is also a vector in Rn, there is a unique linear combination which will give me EI. So let that unique linear combination I'll call BI. Okay, so that implies that I can write down EI is equal to ABI. And this is true for all I is equal to 1 to up to n. Is that correct? And now my job is done. I am there almost, right? So how will I construct matrix B now? How will I construct the right inverse? Almost there, right? Now I'm
The columns
Using
of
the
the
BIs as
matrix B.
columns.
correct. So B I will construct. So this will consider. Let us construct B as B1, B2, up to Bn, a matrix in Rn by n, which is nothing but the columns or the linear combinations B1, B2, Bn, right? To put them in the columns. This is what you do. Then what do you get? Product AB is equal to product A into first column B1, second column B2, and nth column Bn. So what is A into first column B1 will give you? It will give you E1, E2 up to En, which is nothing but identity matrix. That's what you will get. And what does this mean? This means that B is a right inverse. B is a right inverse of A. Correct? So B is right inverse of A, and once you know this is the right inverse of A, then you know that it is left invertible as well as right invertible. So actually B is the inverse of matrix A. Correct? B is the inverse of matrix A. But you have actually proved in case of square matrices, if it is left invertible, then it is right invertible also. And because the matrix is right invertible, you know that the rows of A are linearly independent. So you did not make use of the fact that columns of linearly independent implies that the rows are also linearly independent, right? You actually are able to prove it from this approach also. You could have argued the other way using that basis dimension equality, that at max you will have these many number of things available, but you need some a twist in the argument there. Okay, so this is straightforward. So this proves that B is right inverse of A. So not only it's right inverse of A, in fact it is the inverse of A. And what we did here, have you done something like this before? Have you done something like this before? What I just did here, this in particular, EI is the ith unit vector, and then you write EI is equal to ABI. Have you done this before? This is exactly the same method that you use in your 12th standard to find inverse of a matrix, right? You remember this? This is exact same method I think you used in your 12th standard to find the inverse of a matrix. Okay, so just think about it and see what happens. Okay, so for square matrices, what we have shown. Okay, let us summarize. For square matrices, what we have shown. It is very important that this is done for square matrices. But let us quickly summarize. What is it that we have done? We have shown that left invertibility implies column independence. So this is true for any matrix, but for for the square matrices, this also meant that right invertibility, right? So maybe I will write in the one line, column independence, and this implies right invertibility, correct? And just by taking the transposes, I can do the same argument the other way around. I will start with right invertibility, then that will mean row independence, and that would mean left invertibility. Whatever I did here, it's a square matrix, so I can take the transpose, and by taking transpose, I can run through the same argument once again, and I'll get the same result, right? And right invertibility which implies row independence, correct? This is true for any matrix, but using the similar argument, I can show that that implies left invertibility. So all these concepts are actually equivalent, right? Because we are completing the chain, right? Invertibility will actually imply row independence. It will imply left invertibility, which will tell column independence. So all these four concepts are actually equivalent in case of square matrices. What are the four concepts? The four concepts of right invertibility, left invertibility, row independence, and column independence. All these four concepts are actually equivalent. That's what we will say in case of square matrices. Okay, so this is something that is really very interesting. Okay, so 2 by 2 matrices, 3 by 3 matrices, I suppose you all know. how to find inverses and so on and so forth, right? So we will not go into that. In reality, we will also never find out inverse of a matrix. So we'll come to that shortly. Like how do we really compute? How do we really compute the solution of the system of linear equations? Because for us, inverse is important only from that point of view. How can we compute solution to the system of linear equations? Okay, so that's what we will really get into. So before doing anything further, because we are talking of inverses, I just want to cover another important type of inverse, which is called as pseudo inverse. Okay, which is called as pseudo inverse. So this is also something that is really very important. And now here is a place where I will actually prove the converse also. So far we have seen that matrix A is left invertible, implies that columns are linearly independent. I will prove the converse also here. I'll say that if columns of A are linearly independent, then A is left invertible. I'll prove that. Okay, so let us show something interesting. Okay, so first I will define something which is called as gram matrix. Okay, so this gram matrix is something that is interesting, and I will prove a result. Okay, we first show columns of A are linearly independent. Okay, so I'm starting with a matrix A whose columns are linearly independent. So whenever I'm saying this, immediately you should start visualizing how should A look like. Columns of A are linearly independent, so it can be a tall matrix or a square matrix, right? So that is how this matrix will be. So every time we start talking of these things, you should be able to visualize the sizes immediately. Okay, so it's linearly independent columns if and only if it's n by n gram matrix. It's n by n gram matrix. A transpose A. Okay, A transpose A is invertible. So now, because you are all interested in AI, ML, DL, data science, and so on and so forth, A with linearly independent columns. A with linearly independent columns. What is this A with linearly independent columns? So basically, you have a data set. So consider a tall matrix, right? So the tall matrix that you have, it is like this, right? So this is your matrix A. So along each row, you have certain data points, right? So you have, suppose this matrix is of the size m by n, then you have m rows and n columns. So there are m number of data points, and each data point has some information about n attributes, right? So it is an n tuple. And what are you given? The information is that the columns are linearly independent. That means that attributes are not linearly redundant, right? There is no linear relationship between the attributes. That's what you are told. And then you construct the matrix, which in linear algebra people call gram matrix, which is A transpose A. But yeah, that you know, you can relate it to variance covariance matrix, right? So if you do A transpose A, then that matrix somehow relates to the covariance variance of the attributes, right? So that is something that is important. So you do mean centering and all that stuff, then it will actually exactly be that matrix. So this matrix A transpose A is really very important matrix. It comes everywhere. It will come in regression also. Straight away it will come in regression. So that is the like connection to the data science. Okay, so we'll get into that connection later, but this is just for your information. Okay, so this is something that is given. Okay. So now what we want to prove? We want to prove that if the columns of A are linearly independent, then A transpose A is invertible and vice versa, right? So how do we prove that? So let us first assume that columns of A are linearly independent. Okay. Suppose columns of A are linearly independent. What do we want to show? We want to show that A transpose A is invertible. Okay. To show A transpose A is invertible. Okay. So what do? I have A transpose A, I observe that A transpose A has to be a square matrix, right? So if A transpose A is a square matrix, what are all equivalent conditions of invertibility? All the equivalent conditions of invertibility are listed here. So A is invertible is same as saying A is left invertible, is same as saying A is right invertible, is same as saying rows of that matrix are independent, same as saying columns of this matrix are independent, right? So what I'm going to show here to prove invertibility of this square matrix A transpose A is that I will show that the columns of A transpose A are also linearly independent. Will that suffice? Do you agree it will suffice if I show columns of A transpose A are linearly independent? Then I will show that matrix is invertible. Is that okay? Do you agree? So if I want to show the columns of A transpose A are linearly independent, what am I supposed to do? What am I supposed to do? If I have to show the set of vectors is linearly independent, how do I start? What do I do? I take the linear combination of that vectors to be equal to 0. That's the trivial linear combination, and I show that all the coefficients in that linear combination are 0, right? I hope you are catching up on this now. If you want to show linear independence, how will we show it? Please remember, this is the way. Okay, so what I will start with? I will start with vector x. So let x be a vector. Let x be a vector such that A transpose A into x is equal to 0. By taking A transpose A into x is equal to 0, what am I really looking at? I am looking at linear combination of columns of A transpose A. That linear combination I am looking at. Now, if I am able to show that indeed, if I start with an x such that this is equal to 0, the only possibility for x now is 0 itself. So if x is a 0 vector itself, then can I say that the columns of A transpose A are linearly independent? And because that is the case, we will say that A transpose A is invertible. Okay, so that's what I am going to do. Okay, so this is what I have. So I have this. So I start with 0. So 0 is same as x transpose into 0. X is this vector. And this 0 that is sitting here, I can replace with this. So x transpose into A transpose AX. So again, I use the associative law of matrix multiplication. So I'll have x transpose A transpose into AX is equal to 0, which is nothing but AX, its transpose AX, which is nothing but 2 norm square. So I hope you have seen the lecture that I have already shown, I have already shared with you about the norms, right? Different norms, similarity, concept of similarity, and so on and so forth. So AX transpose AX is 2 norm of AX square. And now we are saying that this 2 norm is 0. So this argument will imply that AX has to be equal to 0. The norm of vector is 0. AX is a vector. So norm of a vector is 0 if and only if vector itself is 0. So AX has to be equal to 0. So this I am going to say implies x is equal to 0. Why will this be true? Ax is equal to 0. This is okay. This is from the property of norm. But why this implication is correct? From here, why can I say x is equal to 0?
Columns of A are
Columns are linearly independent.
Correct. Columns of A are linearly independent. Because columns of A are linearly independent, that tells me that x has to be equal to 0. So I started with a vector x such that A transpose A into x is equal to 0. And that tells me that the vector x has only one possibility, which is x is equal to 0. So if that is the case, that implies that columns of A transpose A are linearly independent. And if columns of A transpose A are linearly independent, then A transpose A is invertible. So one way implication is clear. One way implication is clear to all of you. If columns of A are linearly independent, then A transpose A is invertible, right? Now we prove the other way around. What is the other way around? So do you want me to write this? Okay, let me write this down. This implies that A transpose A has linearly independent columns. And that implies that A transpose A is invertible since A transpose A is square. In general, this is not true, right? you cannot say. But here, because A transpose A is invertible, because it's a square matrix, this is true, right? Now conversely, what do I want to show now? A transpose A is invertible. Conversely, to show A transpose A is invertible, this will mean that columns of A are linearly independent. Correct? This is what I want to show. This is what I want to show. What will I show? This is equivalent to showing negation Q implies negation P. What is negation Q here? If I want to prove the contrapositive of this, what will I really be like to show? So columns of A are linearly dependent. This will mean that A transpose A is not invertible. Is that correct? That's what I will like to show. Okay, that's what I will try to show. And how can I show that? It's very easy actually. So suppose I have columns of A to be linearly independent. So columns of A linearly dependent means that there exists an x not equal to 0 such that Ax is equal to 0. That's what it means to say that columns of A are not linearly independent. Okay, so Ax is equal to 0. This is what I know. So so what I really do is I start with 0. So this 0 is same as A transpose into 0, and then this A transpose, this 0 I can replace with Ax, and then this will be A transpose A into X by matrix associativity. So I have found out a X which is not equal to 0 such that A transpose A X is equal to 0, which implies that columns of A transpose A are linearly dependent. And this will mean that A transpose A is not invertible. Correct? Not invertible. So this kind of completes the proof, right? So what is the proof that we did? The proof that we did is that we first show the columns of A are linearly independent if and only if n by n gram matrix is actually invertible. Okay, now once you know the invertibility of gram matrix, then what is really going to happen? Just one minute extra. Okay, I know the time is up, but only 1 minute extra. Okay, so suppose you have a matrix A. Why this result is important? Suppose we have a matrix A which is of the size m by n, and columns of A are linearly independent. Okay, the columns of A are linearly independent. Then this implies that A transpose A is invertible, right? This is a square matrix and this is invertible. Then define a matrix B which is A transpose A inverse into A transpose. Okay, you define this matrix B to be equal to this. Then is B a left inverse of A? Is B a left inverse of A? What happens to BA? BA is actually A transpose A inverse A transpose multiplied by A. So A transpose A, you can do the matrix associativity like this. So A transpose A is invertible. So you know that this is actually equal to identity. That means that B is actually left inverse of A. So that means that if columns of A are linearly independent, then A is left invertible. And in fact, this is one left inverse that I have actually given you. Okay, so this particular left inverse that I have given you is really very important. It will come in many applications. It has many beautiful, significant implications. So this is called as pseudo inverse. Okay, so this is called as pseudo inverse of it. So we will stop here today, and we will continue with this discussion in tomorrow's class. Okay, but this is called as pseudo inverse of matrix. So any doubt about what we have done so far? Okay, then we can stop here now and we'll continue in tomorrow's class. Thank you.
Thank you, sir.